Hello, in this video I'm going to show you how to find the area under a curve. Not so much an approximation anymore, but how in theory, in a very abstract and general sense, can we turn the ideas we use to approximate the area under the curve into the area under the curve. So here's a nice applet that I found and I sent to you, and it's brought to you by St. Louis University. Thanks guys over at St. Louis University. And this allows you to put in any function and to get a nice visualization, the number of partitions or rectangles, or not even rectangles, could be trapezoids or in fact parabolic arcs, whatever the case may be. But a lot of different options here, a lot of different techniques we can use to approximate. But we're going to stick with rectangles. You know, rectangles are easy, and quite frankly it doesn't matter which technique we use because we're going to work it and apply a limit to it anyway. So that said, here's sine of x for rectangles. We sum those areas using the right endpoint. There's zero height there, and we get an okay approximation. But what happens if instead of 4 I now change that to 40 rectangles? Oh wow, that's a lot better of an approximation, a lot closer to the actual area under the curve. Okay, and we can see these numbers here. We can even change up, use trapezoids. We can use left or right endpoints as far as what we're going to tag for each partition, each subinterval. It doesn't matter. Okay, and well, you know what? That's not good enough. Let's use 400. And what you'll notice is that all of the techniques are going to converge to the area under the curve as the number of partitions or rectangles that we're using, or trapezoids, whatever the case may be, subintervals, gets bigger and bigger and bigger. And so based on the numbers that this great program here is giving me, thanks again St. Louis University folks, it looks like the area under the sine curve from 0 to pi is indeed 2, and in fact it is. So that said, let's figure out a way to generalize that in an abstract sense. So let's kind of get some language down here and some notation and figure out how on earth we can take an approximate value and turn it into the area under the curve. So here's my little sketch, and that's a function f of x, and we're going to assume it's continuous on our closed interval AB, over which we are finding the well, integrating I want to say, but over which that's the interval along which we're finding the area under. Wow, I'm not an English guy. Under that curve, right? So I'm trying to find the area from A to B under the curve f, and f is nice, it's well behaved. So we're going to stick with well behaved functions. So that said, here's the process we've been using thus far, right? We're going to use n rectangles. So we're going to use n rectangles. Okay, we're just generalizing what we've been doing for the last day or so. And here's the thing, they're going to be the same base. So we're going to cut this subinterval, cut the interval from A to B up into n subintervals, or n rectangular, which will actually be the bases of those rectangles, n partitions. And so since they have the same base, note that the length of this interval is b minus a. Right? So the whole interval is b minus a, and if I cut that up into n rectangles, or n partitions, or n subintervals of the same length, then each of those delta x's will be the length of the whole interval from b to a, which is b minus a, over n, the number of cuts you're using, the number of rectangles you're using, the number of partitions, assuming they're all the same length, which we're going to assume that. Okay, so that's going to be the common base of all of those rectangles, those n rectangles. Now the question is, well, how do we get the heights? Well, that's a little more challenging. Recall we've been using this language of tag. So in the first subinterval, in the first partition, the first base, okay, I'm going to tag, let's say, the right endpoint. So I'm going to call that my first tag, and my first tag will be called t sub 1. Now that tag gets thrown haphazardly into the function, which then determines the height. So the height of that rectangle is f of the first tag, wherever that tag may live. It might be the right endpoint, it might be the left endpoint, it might be somewhere along that particular partition, the first base. Okay, it doesn't really matter. Now I'm going to take another tag along the second subinterval, and let's just use the right endpoint again. Doesn't really matter where. I'm going to call that T2, the second tag, in the second partition, second subinterval, second rectangle. Bam! That's the height of my second rectangle, and f of t sub 2. Okay, etc., etc. I'm going to take another tag in the third, call that t sub 3, the third partition, the third subinterval, the third base. Bam! When plugged into the function, that becomes a third. F of t sub 3 becomes the height of the third rectangle. So basically what we're establishing is that the heights are going to vary because our function we're going to assume under which we're finding the area is not a constant. Otherwise we wouldn't need to go through all this mess. We just use an area, a basic known area formula. Who knows, one rectangle or a trapezoid or a triangle. But since the heights are going to vary of all those rectangles, those n rectangles, we have to allow the heights to vary themselves. So the heights are going to be f at the ith tag, and so f of the first tag, f of the second tag, f of the third tag, f of the first tag, height, f of the second tag, f at the third tag, etc., etc. Okay, so that said, we can approximate the area under the curve to be the sum of essentially n, from 1 to n, base times heights. Right? N rectangular areas, base times heights. We have n rectangles, n partitions along the interval a to b, all evenly spaced. Now we're going to rename the base of all those, the common base, the same base, as delta x. Right? There's your common base, which, if you need a formula for, it's just the length of the whole interval from a to b, which is b minus a over n. Okay, so that is your delta x. Okay, the common base for all of those n rectangles. Okay, and it's always the same, by the way in which we set this up. To formalize the heights, well, we're just going to take the heights, which we have right here, and those are f of t sub i's. The tags, the first tag, the second tag, the third tag, but not just the tag themselves. The tags are x values along the x-axis. Oops. Those tags get thrown or plugged into the function and determine the heights. Okay, so here is a nice approximate area under the curve. And so, you know what, I'm tired of approximations. I want the area under the curve. So as we showed in that nice little St. Louis applet, St. Louis University applet, we want the number of rectangles to increase. The more rectangles, the better the approximation, all things held constant. So, you know what, let's turn the approximate into an exact by taking the limit of all of this junk, which is just basically a way of saying the base times heights of all those n rectangles. Here's your base, here are your heights. Right? But the only difference is here, I want an infinite number of rectangles. Okay? I no longer want 4 rectangles or even 400 rectangles. I want the limit of all the base times height, the delta x, which are b minus a over n, times the heights, which are f of each tag. Okay? And when I do take that limit in front, we get the exact area under the curve. So that's the theory. It's a lot of notation. It's the sum of an infinite number of rectangular areas, which are really, really thin rectangles. And one thing to note is that as the number of rectangles increases, the delta x, the basis, is going to get smaller. So that's going to go to 0. It's not going to be equal to 0, but going to 0. Okay, so I want you to digest that. We will apply this tomorrow in class with the help of some fun summation formulas, and we'll look at how messy the algebra is, even for basic problems. And once that becomes a pain in the rear end, I'll show you a nice easy way to another way to find the area under the curve. Thanks for listening. God bless America.